About modeling of future energy systems. I mean, most of the things I've been talking about, I will be talking about, have been talking about over the last 2 years. So what I'm going to do just to step back a little bit and show the big picture and talk about some of the challenges. Does that thing work? No. Oh. Right. So I'll be talking about drivers for power system research, the shape of the current and future power systems. Those things may be quite well known for most of the people interested in power over here, but not for the mathematicians. And I'll do some of the examples of the mathematical and statistical challenges and end up funding opportunities. And then I have a surprise right at the end of the talk. So always, well, when talking about research, it's worth to look at the driver for the power system for the research. And of course, the main driver is something what everyone's been talking about. I've talked about yesterday that any feasible path to 80% reduction, the government target would require total decarbonization of the generation by 2030, which is a pretty ambitious target. So the main thing is obviously grid integration of renewables and the smart grids, and I'll be talking about it a bit later. The second thing, which really not many people talked about today and yesterday, was the rewiring Britain. What I mean by that? Well, the UK energy infrastructure is about 40 years old, and basically, which is lifetime of most of the equipment, and sooner or later it should be replaced. So the question is how to do it. And the second thing is related to renewables. Basically, those renewables tend to be in the places which we don't want them to be, mainly northwest of Scotland. So the question of a lot of investment required to bring them ashore. And quick reminder, because it's about modeling, is how do we do modeling of power systems. I did talk about it yesterday, so just very quickly. So this is the map of the national grid taken. Most of my illustration will be either from National Grid or from Ofgem, so I'm a bit nervous about it. But I hope I put acknowledgements everywhere. So the GB network is about 1,000 nodes and about 1,500 transmission lines, and the analysis is done by algebraic equations, and also for some instances we need differential equations to describe electromechanical stability of rotating generators, and there was a talk about it yesterday. The continental network and the US networks are much bigger, several thousands of nodes. So what's the today power systems look like? So we have a limited number of large controllable power stations. Because they are thermal stations, we can control them. Demand is highly predictable. This is a typical daily demand curve, again taken from National Grid's 7-year statement. So depending on the time of the day, oh, that thing doesn't work, I think. Depending on the time of the day, of the year, sorry, we have a morning peak, then evening peak, and the electricity, the demand drops, which is highly predictable and repeatable. So basically, the whole system operation is demand driven. Whatever demand requires, it is delivered by generation. For modeling purposes, how to run the system, we model only transmission network, which means about this 1,000 nodes in the system, because distribution networks are passive, and they've been over-designed in order to cope with any amount of load that is required from them. And the typical approach is something what I've been talking about yesterday, is deterministic planning and operation. And all of that has served us well for the last, I don't know, maybe 100 years, probably 50, at least 50, 70 years. Coping with contingency is due to this N-1 contingency criterion, again, about which I was talking yesterday when I was talking about the blackouts. So what's the future power system? Again, we've been talking about it for the last 2 days a lot. So it will be probably characterized by the very high number of uncontrollable renewable plants, and what is important, connected at both transmission and distribution level. So one of the main differences is the division between transmission level and distribution level starts to be not as clearly divided as it used to be. Distribution networks start to be also active. So we will have stochastic and highly distributed generation, and what it means we know already. Those kind of slides Mark O'Malley showed today, I showed it yesterday. Generation can go all over the place. It is stochastic, and is stochastic highly distributed. And because that generation is connected distribution level, for a lot of analysis, we need to go into modeling of distribution networks. And this is not a simple task. because distribution networks, I don't know how many thousand, is it tens or is it hundreds of thousands of nodes for the whole UK, but basically it's an order or two order of magnitudes higher task. Now, the next thing is smart metering enabling demand response, which is the smart grids, the famous smart grids. People argue what smart grids are. Well, certainly one useful thing I can say about smart grids is they are very useful to put on any grant application. But what else are they? Well, this is the view from one of those European projects. Again, I showed you about that basically everything is nicely connected together, wind, solar panels, and controlled by some means of communication networks. However, another definition of the smart grid which I like, which I prefer, is this those windmills on top of the cars, and the guy is saying, well, of course, as technology improves, the windmill will get smaller. So I think that's a better definition of the smart grid, and we are working hard to get those windmills smaller. Well, but seriously, demand, the results of all those developments is that demand is not deterministic anymore, and it also becomes stochastic as generation. The next thing is possible electric cars and storage. There's been a lot of discussion about it. From the mathematical point of view, one of the interesting things is that the storage and time shifting of demand creates stronger linkages between time periods in power system models. At the moment, power system models are run from one time instant to the next. When you have time shifting, there are basically linkages which needs to be explored. Now, again, this is a slide nicked from one of the National Grid 2020 consultation document. Basically, electric cars as such do not present a problem, providing when you charge them when there is at night, when there is enough spare capacity in the system. However, if you do them at those peak demand period, then you can create a lot of problem for the system. And the next challenge is interaction with gas and transport networks. Obviously, the generation is partly in gas, and cars means networks, transport networks. So all those things are quite closely connected together. So in short, to summarize those quick review, well, the future power system, one can be say for sure will be more complex and more stochastic. So we need new modeling tools. So what's needed? Obviously, what we need is modeling of highly distributed and stochastic generation and demand. We did some work on generation. The question how to model demand is very much unresolved. So there were hundreds probably of wind studies, what is the wind resource in this country and other countries. What I feel is missing is the stochastic characterization of resource and demand. What are the linkages between the two? The next issue is because of the distributed nature of the generation and demand is we cannot deal with models with hundreds of thousands of nodes and modeling of individual customers. We need tools for aggregation of distribution, generation, and demand, and modeling of interactions between them. So to summarize, basically, what we're talking about is the huge complex system, and something which this morning Sean was talking about. No, sorry, not Sean. Mark was talking about modeling of human behavior. Again, if people don't behave, do not charge, for example, with those cars, don't charge them at night, they can completely wreck the power system. And something what I've been talking about yesterday is probabilistic planning and operation tool. At the moment, it's all deterministic. In the future, we might need probabilistic planning and operation tools, and it is not clear at all how they will work and whether they'll be accepted. And as far as the control is concerned, I mean, at the moment, the centralized power plants, the power plants connected to the system are controlled, basically, because they're controllable. In the future, we might not be able to control them directly, so we might need to move from traditional direct control to stochastic and hierarchical control. And again, it's a big problem. So these are quite general statements. So let me go in more details. Give you some 3 examples of the work I've been involved with in Durham recently. The first is risk calculation and capacity credits, which is the work done by Chris Dent, which is currently on secondment with National Grid, and that links to some extent to the presentation just a few minutes ago for Steve Smith from Ofgem. So the question is, what is the risk of installed generating capacity being inadequate to support peak demand in a system with high wind generation? Actually, the question is more general than that. It's not only peak demand as such, because peak demand may be 1 hour, but it's what is the availability, what is possibility of the generation to support demand over the period of the peak demand, which can be whole winter. So in other words, we can put this question, what is the capacity credit of wind generation? And again, the slide was in the previous presentation. And the work we did, Chris did, was to evaluate the risk of projected fleet of wind plus conventional generation, and calculate the capacity credit is basically is what would be the traditional thermal capacity, which would give the same amount of risk as in the all conventional system. So the graph which you obtain over here, which is not that dissimilar with the graph presented in the previous presentation, I understand that the level of demand, this is effective margin, is about 5,000 megawatts. As you can see, this is a similar shape. It's go up and then goes down. This is without wind. With wind, it's higher. The whole thing is shifted up. It's another way of looking at this is effective capacity credit of wind. So this is over the years. So as you can see, it increases. The value in megawatts increases over the years, while in percentage-wise it drops. It doesn't drop as dramatically as Mark O'Malley was showing this morning in the slide. If you want to ask about that question, why is that? I'm happy to take, or Chris will answer this question after my presentation. The second example is how to model the resource in the system studies. I mean, typical approach is to use hindsight. It means if you want to know what is in the future, basically we use wind data from the past. And there's a famous PORI intermittency study which was published last year, when basically they look at the British and Irish market in 2030, assuming that we have the wind in the year 2000, and they got different results. So there are some examples of the prices and generation. Well, there is nothing wrong with that approach. I mean, it gives robust results because it uses actual wind generation for a particular year, but provides limited insight into what might happen in the future. So what we believe is needed is a stochastic spatial temporal characterization of the resource, how the wind will wing in demand. Yes?
Yeah, and basically there is one part of whether you will discuss it, but there is, well, you seem to go into the modeling or predicting aspect, but things like should the wind generator be connected directly to a grid at all? Questions like this, will they be part of your talk?
Maybe we'll talk about at the end of the discussion, because during discussion maybe just clarification questions. So if we have that spatial and temporal characterization, we could use it for stochastic system studies, and basically that would give us better scientific insight into what drives the result the way it does, rather than just doing results for a particular wind for wind in the particular year. And the next problem is just keeping reserve versus just-in-time delivery. Well, I mentioned yesterday that the way the system is being operated is the certain amount of generation kept in reserve in case something happens, and the same with transmission. And National Grid did study which showed that by 2020, if the current approach is maintained, due to intermittency of wind, there will be almost doubling of so-called short-term operating reserve requirement. This is 4 hours ahead, which shows the red one without wind and the blue one with wind. So almost doubling the reserve. So that is obviously quite expensive, because that reserve is needed 24/7 all the time. So just-in-time approach would be to use flexible demand storage rather than just thermal generation to provide a backup for wind. This is obviously easier said than done, but that must not increase the risk, and the National Grid is from definition a rather conservative body, and quite rightly so, because at the end of the day we need to keep the lights on. So this is quite interesting issue. It requires approach from statistics, stochastic control, because we are talking about stochastic generation and stochastic demand, and operational research. So this is very interesting research issue. And the second challenge, which I will just go briefly through, is that the task of rewiring Britain. The red one it shows the investment in the UK distribution. There was a peak in the 60s. So basically, if we are to repeat the same thing based on the age, it's 40 years. This is the yellow curve, which means we have the peak. We should have the peak about 9. But the question is the age the only thing which tells us about asset management, whether or not we should replace something? And here you have the example of two Richards. Keith Richard on the left and Cliff Richard on the right. And if you look at them, the Cliff Richard seems to be younger than Keith Richards, but apparently it's the other way around. I nicked that slide from Andy Thomas from Central Networks, by the way. So the asset management is important issue. So the replacement must be undertaken in the appropriate way. So we're talking about issues, again, mathematical modeling, condition monitoring, diagnostics, prognostics. It means looking to the future rather than to the past. One problem is that often we have limited information about some of the assets because they are replaced before they fail, so we don't have any failure characteristics. And the new challenge which is coming is reliability of offshore wind farms. And because access to the wind farms is limited, this is big industry, 75 billion industry, reliability may be a bottleneck due to limited and costly access. So involvement of statisticians and mathematicians is required, and we are doing some work on that using Bayesian statistics. Funding opportunities for energy research. Well, actually, as a researcher in energy, I have to say that basically I don't remember we've ever had such a good time. There are plenty of opportunities. The Research Council's UK program is the largest, about 200 million pounds, which is more than all the other programs taken together. And fortunately, UK ERC are very much for interdisciplinary research. It means engineers working with economists, working with mathematicians, working with social scientists. So this is exactly what is required. SuperGen is the flagship initiative, but it's still to be soon to be folded down because it's coming to the end. And now briefly about two initiatives. One is Grand Challenges in Networks, which will look 20, 40 years ahead, and they'll be called, probably announced in the summer. I've been to the workshop when we discussed the areas, and some of those areas which we've talked about probably will be included. Flexible grids, uncertainty and complexity, energy and power balancing. We don't know what the call will look like, but it's quite likely to include those subjects. And the second call, which is out now, which has been out for about a couple of weeks, is Mathematics Underpinning Digital Economy and Energy, deadline of the 1st July again. So this is basically for mathematicians how to model economy and energy problems. So I have a few minutes left. So this is the surprise which I prepared last night. You remember that yesterday Daniel Kirschen was talking about what is reactive power, and he compared it to beer. So because he said, well, actually, those mathematicians and other people perhaps will not understand the full detail of it. So I said, well, actually, I do think that mathematicians, economists, and other are big boys, and they can take the truth. Big boys and girls, sorry, and can take the truth. So actually, I'm going to do a 2-minute explanation, and if someone who understands that wants to buy me a pint of beer afterwards, I'm very much welcome. So what is reactive power? It's not the pint of beer, but you have to think about that guy on the right, which is induction motor. So why we need reactive power? Well, motors are electromagnetic devices and need coils to produce magnetic fields. It's all about electromagnetic induction, Faraday's law. And coils are supplied by current because current is oscillating 50 Hertz. It means that in each cycle, each of the coils is twice magnetized and demagnetized. So that means that energy to magnetize and demagnetize the coils circulates, it oscillates, between the source and the inductor at double 50, means 100 Hertz. And that's all you need to know about reactive power, is that oscillating energy between the source and the load. And it's called reactive power or imaginary power because you cannot use it. Symbol is Q, real power is P. Well, this is one of the confusion with economists, because for economists Q is quantity, P is price, so sometimes we have those problems, which I'm talking about nomenclature. So on average, obviously, the energy transfer is 0. It means you cannot use it for any useful purposes, but it is important to remember that reactive power, those oscillations of energy, are always there in the network. So nasty effects of reactive power: it causes power losses. I square R losses, because there is a flow of energy back and forth, so that's pretty obvious. That means it takes up capacity of wires, because you have to reserve certain capacity for those reactive power transfers. And now the question of the voltage. Well, this is a workshop for mathematicians, so this is one equation which I allowed myself in this presentation. Reactive power flows cause voltage drops, because basically that's the Ohm's law. When you have a flow of current, then that means there's a voltage drop in the network. And if you look at this equation, delta V's voltage drop is proportional to real power and the resistance, and reactive power and the reactance. And the high voltage transmission network X is much higher than R. That means that the voltage drops are much higher due to the reactive power, which means that you cannot transfer reactive power over long distances, because X becomes very high. It's linearly, basically, is a function of the length of the line. And you can compensate reactive power by capacitance. And that's why it is also sometimes called voltage support, because you have improved voltage characteristics. So I think it took 2 minutes and 10 seconds, so I'm sorry, I've run a little bit over time. So conclusions: grid integration, smart grids, and the need to rewire Britain create a huge pool for new research. Collaboration between power engineers and mathematicians, statisticians, and also social scientists is crucial. There are significant funding opportunities, and the most important conclusion is that reactive power is not small beer. Thank you very much.
Congratulations on fitting it in. So time for some questions for Janusz. So one
no.
and then one here. Oh, we don't want one from Mark.
No.
Go on.
I disagree with you on the load. You said it's stochastic. Yeah, or it can become more stochastic. It is stochastic at the moment. If I designed a power system to supply my load, it would be incredibly difficult. The reason we can do it is because I'm part of a population of 4 million people. So it is already stochastic. So I don't agree with you. It won't become more stochastic.
Well, that's aggregation effect, one of the things. That basically is a large population, and you have accuracy of load prediction. I don't know, Andrew Richards is somewhere around here. He will be talking about it, I think, later on today. But basically, it's a pretty accurate prediction, because we don't know. We have a lot of observations from the past. What will happen in the future, we just don't know. This, again, we come back to this question of social science. We don't know how people will respond. It's a big uncertainty. We haven't got a clue how it will look like.
Yeah, but at the moment it's pretty much open loop, and in the future they'll have prices, and therefore we'll probably be able to predict how they even behave even more.
Yeah, but we don't know how they will respond to those prices, and this is your point from the morning. So you are actually contradicting
there might be a
yourself.
sort of two-level answer there. That in short time periods in the future, that being price sensitive for demand will make it more stable. But it may be very hard for us now to predict what the elasticity will be and what the levels will be. So there was a question.
Yeah, David McClellan from Scottish and Southern again. I've got to get hooked in by your description there of the smart grid, make a comment on that, and also a word of caution after that. So the smart grid stuff, it's easy for people to get blown away by all the hype that's going around, and having come from an IET smart grid event today and been at various other ones in the recent past, there is a lot of hype, there's a lot of PowerPoint, there's a lot of vaporware as we refer to it. But it also is possible to find value for money within some of the projects that have been done within the smart grid arena. And I just urge people to look for those and also look for the opportunities further ahead, which will create value. And the second thing was picking up on, you had a comment in there about aggregating generation as it's distributed generation, also aggregating demand. And it's just a word of caution. Some people looking theoretically at the virtual power plant idea get carried away with how it can operate at a higher transmission level. And it's just a word of caution that there are local problems with the distribution networks which have to be taken into account. And the way I would describe it is there's a hierarchy of enough need that we have to satisfy at lower levels before it can play at the top level.
No, that's very much the case. So this is what I meant by problems, that we cannot forget about distribution networks as we used to do, because distribution network used to be over-designed. You just put wires in the ground, cables in the ground, and you can forget about them. Now you can't. And that's the problem. How to look at the problems in the distribution networks, how they affect transmission level, and the other way around. So basically, there's two flows, and you have to get it right, because otherwise you may forget about one of those things at your peril.